There is a question that most people never think to ask, not because it is too difficult, but because it requires standing far enough back from everything, from our planet, our sun, our entire galaxy, to see something that our human lifespans make nearly impossible to perceive. The question is this: are galaxies dying? Not in some distant abstract metaphor, not as poetry, but literally, physically, irreversibly. Are the great cities of stars that populate this universe slowly, quietly going dark? The answer, as best as we can determine from the evidence gathered over decades of observation, is yes. And the story of how and why and what it means, that story is one of the most profound things physics has ever uncovered about the nature of the cosmos we inhabit. We live inside a galaxy. Most of us know this. The Milky Way, a spiral structure roughly 100,000 light-years across, containing somewhere between 200 and 400 billion stars. It is, by any reasonable measure, an almost incomprehensibly vast object. And yet, on the scale of the observable universe, it is one among perhaps 2 trillion such structures. 2 trillion galaxies, each a gravitationally bound collection of stars, gas, dust, dark matter, and the quiet machinery of physics that holds it all together. For most of human history, we looked up at the night sky and saw something eternal, fixed, permanent. The stars were the backdrop of mythology, navigation, philosophy. They did not die on any timescale a human civilization could witness. But what we have learned, particularly over the last 30 to 40 years, is that the universe is not static. It is not a painting. It is a process. And like all processes governed by physical law, it has direction. It moves from one state toward another. And the direction it moves on the grandest scales is toward darkness. Understanding the slow death of galaxies reshapes something fundamental about how we think of existence itself. It tells us that the universe has a biography, a beginning, a middle, and an end, and that the galaxies we see blazing in those Hubble Deep Field images are not permanent fixtures. They are moments. Extraordinarily long moments, yes, but moments nonetheless, caught in the long arc of cosmic time. Before we can understand how galaxies die, we need to understand what sustains them. Imagine for a moment that you were standing in an enormous city, not a city of buildings, but a city of fire. Every structure in this city is a star. Some small and cool and dim, burning quietly for tens of billions of years. Others are massive and brilliant and hot, consuming themselves in only a few million years before exploding in a supernova. This city did not appear all at once. It grew. Slowly over cosmic time, clouds of hydrogen gas, the raw material left over from the Big Bang, collapsed under their own gravity, fragmented and ignited. Star after star formed, and then stars formed from the debris of earlier stars, enriched now with heavier elements forged in those earlier stellar furnaces. This process is called star formation, and it is, in a very real sense, the heartbeat of a galaxy. A galaxy that is actively forming stars is alive, in the way a metabolizing organism is alive. It is taking in raw material, processing it, transforming it, radiating energy. You can see this in galaxies that glow blue and white with the fierce light of young, hot, massive stars. You can see it in the great swirling arms of spirals like our own Milky Way, where nebulae, clouds of gas and dust, are collapsing even now, building new stars, as they have for billions of years. But here's the critical question: what happens when the gas runs out? Stars are made from gas, primarily hydrogen. When there is no gas left to collapse, no new stars can form. The existing stars continue to shine, they will burn through the remainder of their lifetimes, but nothing new is being built. The city is no longer growing, it is aging. Now, a galaxy does not simply run out of gas the way a car runs out of fuel. The process is far more nuanced, far more violent, and far more interesting than that. There are multiple mechanisms by which galaxies are deprived of their star-forming fuel, and physicists and astronomers have spent decades trying to understand which mechanisms dominate, under which conditions, and at what epochs in cosmic history. There is a deep irony at the heart of star formation. The very act of making stars tends to destroy the conditions necessary to make more of them. When a massive star, say 10 or 20 times the mass of our Sun, is born, it radiates so intensely that it heats and ionizes the gas around it. It pushes that gas outward with the pressure of its own light. And when, a few million years later, it exhausts its nuclear fuel and explodes as a supernova, it sends a shock wave through the surrounding interstellar medium that can both trigger new star formation in some regions and completely disperse the raw material in others. A cluster of supernovae, what we sometimes call a starburst event, a period of exceptionally intense star formation, can, through the cumulative energy of its explosions, drive enormous outflows of gas from a galaxy altogether. The very exuberance of star formation carries within it the seeds of its own suppression. Think of it this way. Imagine a fire burning in a room filled with fuel. The fire burns brighter and brighter, but the heat it generates and the pressure of the combustion eventually pushes the remaining fuel away from the flame. The fire, at the peak of its intensity, begins to starve itself. This is stellar feedback, and it is one of the primary reasons that star formation rates in galaxies are not runaway processes. They are self-regulating, to a degree, but they are also, over cosmic time, self-terminating. But stellar feedback alone cannot explain everything we observe. There is another mechanism, one that operates at a scale so extreme it borders on the incomprehensible. At the center of nearly every large galaxy, including our own Milky Way, there sits a supermassive black hole. Our galaxy's central black hole, known as Sagittarius A star, has a mass of roughly 4 million times that of our Sun. It is, by the standards of everyday experience, unimaginably massive, but by the standards of the most active galactic nuclei we observe in the universe, it is relatively quiet, modest even. In other galaxies, at other epochs in cosmic history, these central black holes can be actively feeding, consuming gas and dust that spirals inward towards them, and as that material spirals in, it forms what is called an accretion disk, a swirling structure of superheated matter that radiates with a luminosity that can outshine the entire rest of the galaxy by factors of hundreds or thousands. These are quasars, active galactic nuclei, the most energetically powerful sustained objects in the known universe. And here is the remarkable thing. When a central black hole is actively feeding, it does not just shine, it pushes back. The energy released by the accretion process, carried in jets of plasma that can extend for millions of light years, carried in radiation pressure, carried in the heating of the surrounding gas, can drive enormous quantities of material out of the galaxy. And it can heat the surrounding gas so thoroughly that it becomes too hot and too diffuse to collapse and form new stars. This process is called AGN feedback, active galactic nucleus feedback, and it is now understood to be one of the most important mechanisms by which massive galaxies are quenched, a term astronomers use with quiet precision to describe the suppression and eventual cessation of star formation. The black hole at a galaxy's heart can, in effect, kill its host galaxy, not through violent destruction, but through a slow and systematic removal of the conditions for new stellar life. There is something almost philosophical about this. The gravitational anchor around which a galaxy is organized, the dark, dense singularity at its very core, carries within it the capacity to end the galaxy's productive life. The center consumes the whole.
There is a third mechanism, one that operates not from within a galaxy but from without. Galaxies are not isolated. They exist within a vast cosmic web, a large-scale structure of filaments and sheets and nodes assembled by gravity over the 13+ billion years since the Big Bang. At the densest nodes of this web sit galaxy clusters, gravitationally bound collections of hundreds or even thousands of galaxies, all orbiting within a shared halo of dark matter and permeated by a diffuse superheated gas called the intracluster medium. When a galaxy falls into one of these clusters, when it is drawn in by the cluster's gravity and begins to move through that dense intracluster medium, something happens that physicists call ram pressure stripping. Imagine holding your hand out the window of a moving car. The wind pushes against your hand with a force proportional to your speed. Now imagine that instead of air, the medium through which you are moving is a diffuse but extremely hot plasma. And instead of a hand, what is being stripped away is the cold gas that a galaxy needs to form stars. As a galaxy plunges through a cluster at speeds of hundreds or thousands of kilometers per second, the intracluster medium exerts a pressure on its gas that can literally pull that gas away, stripping it from the galaxy in long tails, like smoke trailing from a candle blown by wind. Remove the gas, and you remove the capacity for star formation. Galaxies that have undergone this process are sometimes called jellyfish galaxies, because in images taken by modern telescopes, you can see exactly this: a galaxy with brilliant blue star-forming knots in its trailing gas, like the tentacles of a jellyfish, with the galaxy's disk above it increasingly red and quenched, stripped clean of its future. It is one of the most visually striking demonstrations in all of observational astronomy of physics operating in real time. Now I want to pause here because there is something important that is widely misunderstood, even among people who follow science carefully. When we talk about galaxies dying, there is a tendency to imagine something dramatic, an explosion, a collapse, something visible. The word death carries with it connotations of suddenness. But the death of a galaxy is almost nothing like that. Here is the counterintuitive truth. A quenched galaxy, a galaxy that has stopped forming stars, does not disappear. It does not go dark immediately. It continues to shine for billions of years with the light of its remaining stars. But those stars are growing older. The most massive ones have already ended their lives. The mid-mass stars are slowly exhausting themselves. What you are left with in a quenched galaxy is predominantly old, cool, red stars, the long-lived, low-mass stars that burn slowly and quietly for tens of billions of years. This is why astronomers speak of the red sequence. When you look at a color mass diagram of galaxies, essentially a census of galaxies plotted by their color and their mass, you find a striking pattern. There is a blue cloud of actively star-forming galaxies, and there is a red sequence of quenched, passively evolving galaxies, and the red sequence is heavily populated by the most massive galaxies in the universe. The most massive galaxies quenched earliest.
They built up their stars rapidly, in a furious burst of formation in the early universe, and then, suppressed by AGN feedback, by the sheer violence of their own black hole's energy output, they shut down. They have been coasting ever since, slowly reddening, slowly aging. The common misunderstanding is that these red elliptical galaxies are somehow young or new. In fact, many of them are the oldest stellar populations in the universe. Their stars formed when the cosmos was less than a few billion years old. What we see now is the afterglow of creation that happened long ago. A quenched galaxy is not a galaxy that never lived. It is a galaxy that lived intensely and early and has spent the bulk of cosmic time slowly, quietly dimming. There is another misunderstanding worth addressing. Many people assume that our own galaxy, the Milky Way, is safely, robustly alive and will remain so indefinitely. And in the context of a human lifetime, this is true. The Milky Way is still forming stars. It will continue to do so for billions of years. But the Milky Way's star formation rate has declined significantly over cosmic time. In its youth, around 10 billion years ago, our galaxy was forming stars far more vigorously than it does today. The rate has been falling, not dramatically, not catastrophically, but falling. And in the future, particularly after our collision and merger with the Andromeda galaxy, expected in roughly 4 to 5 billion years, the dynamics will change substantially. Mergers can trigger intense bursts of star formation, consuming remaining gas reserves rapidly. After such a burst, the merged system may quench. The galaxy that results from the collision of the Milky Way and Andromeda may end as a large elliptical, red, quenched, slowly fading, a monument to what was. We are not outside this story. We are inside it.
Let me step back now from the mechanisms, from the physics, from the observational data, and simply reflect on what all of this means. We exist at a particular moment in cosmic time, approximately 13.8 billion years after the Big Bang. And this moment, it turns out, is not in the middle of the universe's productive life. It is past the peak. Astronomers have measured the cosmic star formation history, essentially a record of how many stars were being born per unit volume of the universe at every epoch in cosmic time. What they find is this: star formation peaked approximately 10 billion years ago. At that time, the universe was forming stars at a rate perhaps 10 times higher than it does today. Since then, the overall rate has been declining, slowly but consistently. The universe, in a very real sense, had its youth. It had its productive prime, and we are living in what cosmologists sometimes call the stelliferous era, the era of stars, but we are in its later chapters, not its opening ones. This is not a cause for despair. It is, I would argue, a cause for a particular kind of wonder. We exist in a universe that has structure, that has a narrative, that has the kind of temporal arc that we recognize from the lives of living things, from the rise and fall of civilizations, from the rhythm of the seasons. The universe is not a static backdrop. It is a story, and it has a direction.
The galaxies we see, the ones that look so permanent in long exposure photographs, those vast islands of light scattered across the darkness, are all at various stages of that story. Some are young and blue and furiously productive. Some are old and red and passively aging. Some are being quenched even now, their gas stripped away by their passage through a cluster, their central black holes shutting down the machinery of starbirth. In the very long run, on timescales of trillions of years, the last stars will burn out. Not all at once. The smallest stars, the red dwarfs, will persist for perhaps 10 trillion years, glowing dimly and quietly long after everything else has faded. But eventually, they too will exhaust their fuel, and what remains will be a universe of black holes and neutron stars and white dwarfs slowly cooling toward the ambient temperature of a near-empty cosmos. No new light, no new warmth. The long, cold afterward. This is not science fiction. It is the straightforward extrapolation of known physics into the deep future. But here is what I find most profound about all of this, and I want you to sit with it for a moment. We are made of star stuff. This is not a metaphor. The carbon in your cells, the oxygen in your lungs, the iron in your blood, these elements were forged in the nuclear furnaces of stars that lived and died before our solar system formed. Stars that were born in the same process of gas collapse that we have been discussing. Stars that exhausted themselves, that gave back to the interstellar medium the enriched material from which later generations, including the generation that built us, were made. We are, in a very literal sense, the product of that star formation history. We are the consequence of the universe's productive era, and we exist right now in this relatively narrow window of cosmic time when conditions are still favorable for complexity, for chemistry, for biology, for consciousness. The fact that we can look outward and measure the fading of the cosmos, that we can construct a history and a future for the universe from the light that has traveled billions of years to reach our instruments, is itself an extraordinary thing. The universe has produced in us a mechanism by which it can observe its own aging. Somewhere in a galaxy cluster hundreds of millions of light years away, a spiral galaxy is falling inward. It has been falling for hundreds of millions of years, drawn by the gravity of the cluster, moving at a speed of 1,000 kilometers per second through the hot plasma that fills the space between galaxies. Behind it, trailing like smoke, is a stream of gas, the raw material it once used to build stars, now torn away. In that trailing stream, here and there, knots of gas are dense enough and cool enough to collapse, and they are doing so, forming stars even as they are being stripped from the galaxy that gave them birth. Stars being born in the act of the galaxy's own disassembly. The galaxy itself, now stripped of most of its cold gas, is slowly reddening. The blue light of young stars is fading. The red light of old stars is all that remains.
It is still billions of stars. It is still immense, but its active life is ending. No one lives there, as far as we know. No one watches this happen from the inside. No one mourns. But we, from our small planet around an ordinary star in a not yet quenched galaxy, can look outward and see it. We can measure it. We can understand it. And in understanding it, we are doing something that the universe, for most of its history, could not do. We are bearing witness. If this journey through the long death of galaxies stirred something in you, a question, a sense of scale, a quiet reckoning with just how extraordinary it is to exist in this particular window of cosmic time, then consider subscribing. Not because new videos arrive constantly, but because when they do, they will ask the same kinds of questions this one did. The deep ones, the ones that require standing far enough back to see the universe whole. Share this with someone who thinks carefully about the world. Leave a comment not with what you felt, but with what you now want to know. That curiosity, that reaching outward, is precisely the thing that makes us worth the universe's attention.